Hello everyone, welcome to Chem 9. Today we will begin chapter number 3. In this chapter we will learn about uh, ionic and covalent compound. There are two kinds of ionic compounds which we will discuss. First kind is those ionic compounds which contains monoatomic ions, and the second uh, kind of ionic compounds are those which contain polyatomic ions. And then we will learn about what are covalent compounds, and finally we will learn how to write Lewis structures of covalent compounds. So let's begin chapter number 3. Okay, so before we discuss about what are compounds, let's review one more time what are elements. In previous chapter we learned that elements are that kind of matter which is made up of one type of atom or atoms. For example, if I have a helium gas in a balloon, so that gas is made up of only helium atoms. So if red sphere represents the helium atom, so this would be an example of element, right? Another example would be the gas we breathe, oxygen. So oxygen, the formula is O2, but it's made up of only O atoms. So O2 means two atoms are connected together or bonded together. So if we have an oxygen gas, so that's what it would look like. So each blue sphere represents, in this case, oxygen. So oxygen is also element. So that's the definition of element. So element is that kind of matter which is made up of only one type of atoms. So all elements are listed in a periodic table. Now, what is compound? Compound is another kind of matter which is made up of, so compound is also a matter, but its compound is made up of two or more type of atoms. That's first condition. And second condition is the atoms are held together by chemical bond in a compound. So compound is a type of matter which is made up of two or more different type of atoms, and atoms are held together by bonds. One of the simplest example of compound is water. In case of water, water is made up of hydrogen atom and oxygen atom. So where red spheres are hydrogens and the blue one is oxygen. So this would be water. So HOH. Now because water is made up of two type of atoms, hydrogen atom and oxygen atom, therefore water is a compound. Another good example is this molecule of caffeine. This is the molecule which is present in coffee or tea or many other caffeinated drinks. Caffeine gives us energy boost. The detailed action of caffeine we will learn in the biochemistry portion of this course. But for now, just remember that caffeine is also a compound, and as we can see, it is made up of multiple atoms, but uh, all those atoms fall in four types. So the gray atoms are carbon atoms, so it has multiple carbon atoms. Blue are nitrogen, white are hydrogen, and red are oxygen. So because this molecule is made up of more than two different type of atoms, therefore it's a compound. The lines you see in the middle, these are chemical bonds. chemical bonds hold the atoms together in a compound. There are two types of chemical bonds. The first type is ionic bond and the second type is covalent bond. Ionic bonds are those type of chemical bonds in which valence electrons are transferred. We will learn more about this in coming slides. And covalent bonds are those type of bonds in which valence electrons are shared. All compounds which are held together by ionic bonds are known as ionic compounds, and all compounds which are held together by covalent bonds are known as covalent compound. There are 118 elements known to us. On the other hand, there are hundreds and thousands of compounds known to us. A lot. So that means that there are a lot of compounds as compared to very few elements. So now the question arises, why there are so many compounds? Or in other words, why do even compounds form? In previous slide, I gave you an example of water molecule or water as a compound. So water is made up of hydrogen atom connected with oxygen. In fact, two hydrogen atoms connected with one oxygen atom. So this is water as a compound. So why these different type of atoms uh, combine to form a compound? Why can't they just stay separate? Why couldn't oxygen atom and hydrogen atom stayed as an element? Why do they even combine to form the compound? It is all about stability. In chapter number 1, we learned that any substance, if it has higher potential energy stored in it, it becomes unstable. And if a substance has a low potential energy in it, it will be more stable. When compounds are formed, they have lower potential energy than the separate atoms. So in other words, if elements stay as separate elements, they have high potential energy. And once they combine to form a compound, the compound has low potential energy. Low potential energy means it's more stable. And in this universe, all systems go towards stability. Or in other words, any system or any process which loses energy and becomes more stable will be spontaneous. Or in other words, it will take place. When compounds are formed, atoms with partially filled valence shells, for example, in this case, hydrogen and oxygen, they have partially filled valence electrons. So these partially filled valence electron kind of atoms will attain the filled uh, status and they become stable when they form compounds. So after they form chemical bonds and become become a compound, uh, these atoms in a compound attain a noble gas kind of configuration. We will learn in more detail in coming slides what do I mean by noble gas configuration and how do they attain it. But for now, just remember that individual elemental atoms, they are unstable because their valence shells are not completely full. And when they form a compound, their valence electron becomes full, and in doing so, they achieve stability. And that's why compounds are formed. In the beginning of this chapter, we learned that there are two kinds of compounds, ionic compounds, and the second one is covalent compounds. Let's start our discussion with ionic compounds. Ionic compounds are also known as salts. In our daily life, we call table salt a salt. Table salt is also an ionic compound and its formula is NaCl, it's sodium chloride. But in chemistry, we call all ionic compounds as salts. Ionic compounds are those compounds which are composed of oppositely charged ions. For example, sodium chloride is made up of sodium positive and Cl negative. Any species which has a charge on it, whether its charge is a positive charge or negative charge, we call them as ions. And any compound which is made up of ions, that compound is known as ionic compound. In all ionic compounds, we will have oppositely charged ions connected to each other, such as sodium positive and Cl negative connected to each other to form sodium chloride. That is one of the most common ionic compound. The simplest ionic compounds are those compounds in which we have monoatomic ions. What's the meaning of monoatomic ions? Mono means one and atomic means atoms. So monoatomic ions means those ions which are made up of one atom. For example, sodium positive, that's a mono, means one atom ion. So monoatomic ion. Similarly, Cl negative is also monoatomic. And whenever uh, opposite charges are together, we know opposite charges attract each other. So this force of attraction, positive charge, so this force of attraction is ionic bond, because ionic bond is not a stick or is not some kind of a rope which holds these ions together. Bond is a force or a force of attraction which keeps these ions together, and this, in case of ionic compound, the force of attraction is the attraction between the positive charge and the negative charge. Monatomic ions are formed when a metal loses an electron, uh, and that electron is absorbed by a nonmetal. Let me explain with the help of an example. Let's say, for example, we have sodium atom, and from periodic table we uh, have learned that sodium has a nucleus, and nucleus contain 11 protons. So nucleus contains 11 protons, and each proton has one positive charge. Therefore 11 protons will have 11 positive charge. Now sodium has 11 protons and therefore it has 11 electrons. Neutrons do not play any role in this, so I'm not gonna worry about neutrons. So the nucleus of sodium has 11 protons, therefore the charge is 11 positive. And around the nucleus, we have 11 electrons somewhere. They are not symmetrically distributed as I'm showing, but there are 11 electrons. I guess this is 11. So overall, there is 11 positive and 11 negative. So therefore, overall in this sodium atom, the positive and negative cancel each other out. So it's neutral. Overall, there is no charge. However, if one of the electron is lost, so one of the electron is lost. So now sodium will have still 11 protons in the nucleus, but only 10 electrons around it. I'm not going to draw 10, but 10 electrons. So now sodium has 11 positive charges and 10 negative charges. So combined effect will be that it will have one positive overall charge. So whenever an atom loses an electron, it will get a positive charge. So loss of electron will result in positive charge. The species with a positive charge is known as cation. So when sodium atom loses an electron, it becomes a sodium cation. Okay. Similarly, if a non-metal gains an electron, for example, if I have fluorine, fluorine has 9 protons and 9 electrons. So it has 9 protons and 9 electrons. So in its nucleus it has 9 protons, and around the nucleus it has 9 electrons. So overall 9 positive and 9 negative. So when overall it's neutral, no charge. But when non-metal absorbs one more electron, then it will become, number of protons will still be 9, but because it has absorbed an extra electron, therefore it will have 10 electron around it now. So overall charge will be 9 positives and 10 negatives, so it will be -1. So any species which has a negative charge is known as anion. So fluorine atom, when it absorbs an electron, becomes a fluorine ion. We call it a fluoride ion uh, or fluoride anion. Ion is a general term. Any species which has a charge, whether it's a positive or negative, we call it ion. But the specific term is cation for positive charge and anion for negative charges. This figure shows you the formation of ionic compound, and it also explains the principle of formation of ionic bond. So neutral atom, when they gain electron, they form negative charge ion, as we learned in previous slide in case of fluorine. And similarly, when neutral metal atoms, they lose electron, they become positive charge cation. So for example, in this case, we have a sodium atom. So sodium atom, as we know, it has 11 protons and 11 electrons around it. So it's neutral. At this stage, it's neutral. But then it loses an electron. If it loses an electron, now it still has 11 protons, but it has only 10 electrons. So 11 positive charges and 10 negative charges. So overall, sodium gets one positive charge. So we call this cation. So it's a sodium cation. Now, because sodium lost an electron, where did that electron go? Electrons do not hang around in the air. So if someone loses it, that electron will be absorbed by some other atom or element. So for example, in this case, we have chlorine atom nearby. So chlorine atom has 17 protons and 17 electrons. So it's neutral. At this stage, it's neutral. But after it absorbs an electron or gains an electron, where did this electron come from? It came from sodium because sodium lost it. So after it gains the electron, now it has 18 electron because it was 17, gained 1, so it's 18. Protons are still 17. So overall there is one extra negative charge. So therefore it becomes a negatively charged species. We call this anion. So sodium is positive charge, nearby chloride is negative charge, and we know that opposite charges attract each other. and in fact it's a strong attraction, and this strong attraction between opposite charges is known as ionic bond. And please remember that when this process takes place, the loss of electron, we don't have only one atom, we have multiple atoms, sodium atoms which lose electron, and multiple chloride atoms which gain electron, and all of them uh, come together to form a ionic structure. It's called a crystalline structure, so it's a crystal, so it's a sodium chloride crystal. So in crystal, what happens is we have a positive charge, and then we have negative charge, then we have another positive charge. So it's a ordered structure. And why do they form this structure? Because it gives them stability. So all positive charges are sodium, so one positive, one negative, one positive, one negative. So overall they have a symmetrical structure. It's a crystalline structure. One key thing is that the number of positively charged and number of negatively charged ions will be exactly the same. If in a crystal we have 100 sodium ions, we will also have 100 chloride ions. So in other words, the ratio is always going to be 1:1. So in the formula, we just report the whole number ratio. So NaCl, this formula does not explain how many total sodiums and total chlorides are in a crystal. What it explains is that the ratio between sodium ions and chloride ions in a crystal is 1:1. The strong attraction between the sodium positive charges and the negative charge from the chlorine uh, is uh, is the glue that holds these ions together. So in other words, the ionic bond is the strong attraction between the oppositely charged ions. And this is a central theme in chemistry and physics. That is, the oppositely charged species attract each other and the same charges repel each other. The net charge in this crystal, the net charge is 0. 0 means overall it does not have any charge, because the positive charge of sodium is neutralized by the negative charge of chloride. So after the crystal is formed, the charge is neutralized, so net charge will always be 0. Ionic compounds have very different physical and chemical properties than the element from which they are formed. For example, in case of the element sodium, as shown here, so this is sodium metal. So sodium metal is a shiny, soft metal. It is quite reactive, and it is a flammable metal. It explodes if it comes in contact with water. So it's quite dangerous metal. Uh, at the same time, chlorine gas is a noxious gas, and it's poisonous or toxic, and it can be quite dangerous at high concentrations. And but when they combine with each other, they produce sodium chloride. And compared to the parent elements, sodium chloride is quite harmless. In fact, sodium chloride is one of the essential nutrient. And we consume sodium chloride every day in our food. Uh, so now you can see that the properties of the compound is quite different from the parent elements from which it is formed. Ionic compounds are held together by strong attraction of opposite charges. For example, in sodium chloride, we write sodium chloride as NaCl, but we know that Na has a positive charge and Cl has a negative charge. And these opposite charges, they have a strong force of attraction uh, with each other, because we know that opposite charges attract each other, and therefore they come together. And once they come together, so they form the compound, And now the charges disappear. Why? Because opposite charges, they neutralize each other. So the force of attraction which keeps these two oppositely charged ions together is known as ionic bond. So the net charge is equal to 0, which is because the opposite charges, they neutralize each other, they cancel each other out. When a cation and anion has same charges, the ratio will be 1:1. What does that mean? So that means is that as if the charges are same, for example, in case of sodium is 1 positive and 1 negative, right? So same charges. So when they combine, so the ratio will be NaCl. So one sodium will neutralize one chloride. However, if the charges are not the same magnitude, for example, sodium is 1 positive and sulfur is 2 negative. So now one sodium is not enough to neutralize the sulfur. Why? Because sulfur is 2 negative. So in order to neutralize, we need 2 sodiums, because together 2 sodiums will have 2 positive charge and one sulfur will have 2 negative. So now they will neutralize. So in this case, the ratio will be Na2 and S. So this 2 means that we needed 2 sodium ions to neutralize 1. Whenever there is nothing here, that means 1. So we call these tiny numbers as subscripts. And subscripts represent how many ions of any element are present in that ionic compound. So if you see a formula something like CaCl2, that means for every 1 calcium we need 2 chlorides to neutralize it. Ions play extremely important role in our body. Any ion which when dissolved in water, it will conduct electricity, and those ions which conduct electricity when dissolved in water are known as electrolytes. And electrolytes play important role in human body. All the signals from the brain uh, to different parts of body such as muscle and other vital organs, those signals are electrical signals, and ions or electrolytes help all those signals to transfer from brain to rest of the body. So they play important role in regulating important functions of various organs. Some of the important monatomic ions which play important role in our body are sodium, potassium. So sodium, potassium regulate blood pressure. Calcium, it plays important role in the bone health, and chloride. Uh, so these are few important monatomic electrolytes in our body. So far, we have learned that ionic compounds are made up of positive ions and negative ions. And we have also learned that positive ions are formed when metals lose electrons, and negative ions are formed when nonmetals gain electron. The example I showed you earlier was the case of sodium, where sodium lost one electron and it became sodium positive ion or sodium cation. Now you may ask, can sodium lose 2 electrons and become sodium 2 positive? Because some metals do have a 2 positive charge. Can it lose 3 electrons and become sodium 3 positive? If not, why? And how do we know that which metal gonna lose how many electrons? The answer to all these questions can be found in a periodic table or from the periodic table. The periodic table can be used to determine the charge as well as the magnitude of cations formed from the main group elements. So what are main group elements? So main group elements are those elements whose group number has a letter A on top of it. For example, 1A, 2A, 3A, 4A, and so on. These middle groups, they have letter B. These are transition metals. So the information which I'm gonna provide you right now is valid only for the groups which has the letter A with their group number. So let's talk about group number 1A, 2A, and 3A. Please remember that the group number 1A, 2A, 3A can also be used to signify how many valence electrons they have. For example, any element in group 1A has one valence electron because they are in group 1A. That's how they are arranged. They are arranged based on their valence electrons. All elements in group 2A has two valence electrons. So all elements in group 3A has three valence electrons, and so on. When metals from group 1A, 2A, or 3A lose electron to form cations, they lose all valence electrons. Now in case of group 1A, they have only one valence electron, so the maximum number of electrons these metals can lose is 1. Hence sodium, because sodium is in group 1A here, it has only one valence electron, therefore it can lose only one electron. So the other possibilities are not possible. So sodium can never have two positive charge or three positive charge. So only charge sodium can form is one positive. So let's get rid of the other incorrect possibilities. Similarly, if calcium metal loses electron and form calcium cation, how many electrons is gonna lose? All we need to do is we need to find where calcium is. Calcium is here. And what is the group number? Group number is 2A. So because group number is 2A, how many valence electrons calcium has? It has two valence electrons. So therefore it's gonna lose two electrons. If an element loses two electrons, the charge will be 2 positive. Not only calcium, every metal in group 2A will lose two electrons and they all will get two positive charge. So to make it easy, how can we figure out what will be the cation charge? Cation charge will be same as the group number. So if a metal is in group 1A, it will form one positive charge. If metal is in group 2A, it will form 2 positive. If metal is in group 3A, it will form 3 positive. When these elements from group 1A, 2A, and 3A lose their valence electrons, the resulting electron arrangement in the ion is same as the nearest noble gas, and noble gases are stable. Therefore once the elements lose electron, they become similar to noble gases, or in other words they also become stable, and that's why they lose electrons, because they become stable. There are two notable exceptions to this cation formation. One of the exception is beryllium in group 2A, and the other one is boron in group 3A. Beryllium and boron, they do not like to lose electron, so hence they do not participate in ionic compound formation. In previous chapter, we learned that atoms have electrons arranged around the nucleus in various energy shells or energy levels. So these are the energy levels. And we also learned that electrons at the lower energy level are more stable, and as it goes uh, higher up, the energy of those electrons increases, or in other words, they become more unstable. And this figure shows the energy level diagram for neon atom. And we know that neon is a noble gas. It's one of the most stable element. So it's a noble gas. We also know that each energy level has a maximum occupancy rule, which can be calculated by the formula 2n square. It means the total number of electrons which can be on any level can be calculated by 2n square, where n is the number of the energy level. For example, for first level, n equals 1. So therefore 2n square will be 2 times 1 square, it is 2. So it means on first level maximum number of electrons can be 2. Similarly on second level maximum number of electrons can be 8. Neon atom has 8 protons and 8 electrons. So protons are in the nucleus, but excuse me. So neon atom has 10 protons and 10 electrons. All 10 protons are in the nucleus. However, electrons are in various energy levels. Out of those 10, the first 2 are in the first level and the remaining 8 are in the second level. We also know that 8 is the completely full, because maximum number of electrons on the second level can be 8. Therefore neon has a full second level, and neon also has a full first level. In other words, neon atom has both energy levels completely full. It turned out that when atoms have completely full energy levels, they become extremely stable. Let's look at the sodium sodium energy level diagram. So in case of sodium, sodium has 11 protons and 11 electrons. All 11 protons are in the nucleus, but the 11 electrons are distributed in these energy levels. So we know that the maximum number of electrons can be 2 on the first level, so that's there. Second level can be maximum number of electrons be there is 8, so that's 2 here and 8 here, that's total 10, and sodium has 11, so the last electron has to go to number 3. Now because of this, the last electron, the number 3 shell is not completely full, and because all the shells are not completely full, therefore sodium is not stable. Now what happens when sodium loses electron? So sodium loses this electron. So when this electron goes out, sodium becomes sodium ion. So let's see what happened to the energy level diagram of sodium positive. So now sodium positive ion, because this electron is not there anymore, so it has only 2 levels, and these 2 levels are completely full. And if you look closely, this is exactly same as neon. So the total number of electron is same as neon. And we know neon is stable, and sodium positive also has a similar shell configuration as neon. Therefore sodium positive is also stable, and that's why sodium atom loses electron in order to become stable sodium positive ion. Now if we look at the case of magnesium, so we will see magnesium has 12 electrons, so therefore first level has 2, second has 8, the final 2 electrons has to go to the last or the third energy level. Because the third energy level is not completely full, therefore magnesium atom is not stable. In order to become stable, it needs to get rid of these. So when it gets rid of these two electrons, it becomes magnesium 2 positive, and in magnesium 2 positive the electron configuration is same as the nearest noble gas, which is neon, and magnesium 2 positive is stable. So now we know why magnesium loses 2 electrons, because after losing 2 it becomes stable, and why sodium loses only 1, because that's what it needs to do to become stable. Group 4a and transition metals do not lose all their valence electrons in becoming cations. Uh, so therefore their charge is less predictable. So we cannot really tell whether they're gonna lose 1 electron or 2 or 3. So we can't really say for sure if the charge will be 2 plus or 3 plus. And furthermore, many of these metals can lose a variable number of electrons. For example, iron can also lose 2 electrons to become 2 positive, or it can also lose 3 electrons to become 3 positive. So for example, in case of 1a elements such as sodium, we know that sodium only gonna lose 1 positive. So sodium will always be 1 positive because we know it's only gonna lose 1. But if iron loses electron, we don't know whether it's gonna be 2 positive or 3 positive. We don't know for sure. So therefore, in order to uh, specify what charge it's gonna lose, so we specify with the use of Roman numeral. For example, if iron loses 2 electrons to become 2 positive, so we call it iron 2 cation. But here we just call it sodium cation because we know sodium is always 1 positive, right? So similarly, this one will be iron 3 cation. So in case of transition metals, we use this Roman numeral to specify what is the charge. If I read somewhere magnesium cation, now I know magnesium is in group 2a and 2a loses 2 electrons. Therefore, from this I can for sure figure out that magnesium is 2 positive, right? But on the other hand, if I read gold cation, now gold is in transition metal, so I don't know because gold could be 1 positive, 2 positive, or 3 positive. So this is a wrong or incorrect information or incomplete information. So in case of gold or any other transition metal, so we must use Roman numerals. So for example, gold 2 cation. So now I know that uh, this cation is 2 positive charge. There are 2 exceptions in transition metal. Those two are silver and zinc. Silver is always 1 positive and zinc is always 2 positive. So therefore we do not use the Roman numeral to specify the silver and zinc. So silver 1 is incorrect because we only use this Roman numeral when there is a possibility of different kind of charges. But silver always form 1 positive, so therefore we just call it silver ion. We don't call it silver 1. Similarly, zinc is always 2 positive, therefore we just call it zinc ion or zinc cation. This table specifies what kind of charges are formed when certain metals and non-metals gain or lose electrons respectively. So you can see all elements in group 1A has one positive charge. All elements except the first one, which is beryllium, have two positive charge, and metals in group 3A has three positive, and the rest of these, so they have multiple charges. So iron could be two positive, three positive, and this is tin 2 positive, tin 4 positive. So all of these where there are multiple charges, we use Roman numeral. So for example, the name of magnesium 2 positive is just magnesium cation, but the but for cobalt, it's either cobalt Roman numeral 2 or Roman numeral 3, depending on which one we are talking about. Lead and mercury are often referred as heavy metals uh, because they have relatively high atomic number. These metals form uh, different kind of ions such as lead 2, lead 4, mercury 1, and mercury 2. Lead 2 means lead has a 2 positive charge, or lead 4 means the lead ion has a 4 positive charge. For example, lead 4 will be Pb4 plus, and so on. So these lead 2 and mercury 1 are poisonous heavy metal cations, and they are especially harmful to developing a brain of a child. Lead poisoning can occur when a child is exposed to the dust from old lead-based paint, uh, which was used in houses built before 1978. For this reason, lead 2 containing compounds are no longer added to paint. Similarly, the fuel which we use in our vehicles, if you check, you will see unleaded fuel, because before 1978 they used to add lead in the fuel because it would make engine run smoother, but later it was found that the lead was so toxic that it was uh, causing many brain issues in kids. So therefore lead was banned. So after that, all the fuels are unleaded fuels, means they don't have any lead in them. Lead and mercury are also banned in all other consumer products. Let's take a look at electron configuration of non-metals from groups 5A, 6A, and 7A. Remember, in case of sodium and magnesium, these two metals had extra electrons in group number 3, which were making them unstable. Now, the situation here in case of non-metals is different. Now, for example, fluorine, it has two electrons in the first valence shell, or sorry, it has two electrons in the first energy level. Remember, fluorine has total 9 electrons. So therefore, in the second level, it has only 7 valence electrons. And remember, in order to be like a noble gas and fill up the entire energy level, you need 8 electrons. Therefore, fluorine atom is not stable because it does not have a completely full second energy level. So in order to completely fill this level, fluorine needs to gain 1 electron. So when it gains the electron, it becomes fluoride ion. In fluoride ion, now it has 8 valence electrons in the last or the second shell, and after it gets the 8, it becomes similar to the noble gas neon, and it becomes stable. So hence, in case of noble gases, the situation is completely different from metals. Metals had 1 or 2 extra electrons in the last shell, which they get rid of and they become stable. However, in case of non-metals, they are losing, or they are already short on electrons, so they cannot lose electron. Instead, they need to gain electron, and hence when they gain electron, they become negatively charged because now they have more electrons than protons. The whole idea or whole purpose behind losing or gaining is to achieve electron arrangement same as the nearest noble gas, because once they achieve configuration same as noble gas, they become stable. And as I mentioned earlier, every species want to be stable, or every system in this universe want to become stable. So we learned that it's easy to calculate the charge of cations when a metal loses an electron. For example, 1A metals always get 1 positive, 2A metals get 2 positive charge, and so on. Similarly, how do we calculate the charge on non-metals? In case of non-metals, is relatively easy to calculate the charge. So the charge of anion from a non-metal is equal to group number minus 8. So for example, fluorine is group 7A. So fluorine is in group 7A. So the charge on fluorine is 7 minus 8 equals -1. So this way we can calculate the charge on non-metals. So this table shows us the charge of non-metal anions when they gain electron. And remember, charge of anion is equals to uh, group number minus 8. So for example, if we want to calculate the charge on sulfur, so sulfur is in group 6. 6 minus 8 is -2. Therefore, charge on sulfur is -2. Similarly, charge on oxygen is -2. So any element or any non-metal from group 5A will need to gain 3 electrons. Therefore, charge will be 3 negative or -3. And all element from 7. So 7 minus 8 would be -1. So all of these are -1. In case of metals, it was easy to name the metal cation because it's same as the element name. For example, this is sodium, and when sodium loses electron and becomes a cation, we call it a sodium cation. Okay, same as that. However, in case of non-metal, the naming is slightly different. So in case of the ions formed from non-metal, what we do is we change the name and we add "ide" at the end. For example, chlorine is Cl. When chlorine atom loses an electron and becomes a ion, we call it chloride. So we remove the last 3 letters and we add "ide" at the end. So chlorine becomes chloride ion. So fluorine will be fluoride. Oxygen, so if it's just an atom, we call it oxygen atom. But when it loses gains the electron and becomes a ion, we call it oxide. So oxygen becomes oxide, sulfur becomes sulfide, phosphorus becomes phosphide, nitrogen becomes nitride. Let's take a look at few examples. First example is, what ions are formed when cesium transfers electron to bromine? Cesium is Cs and bromine is Br. Cesium is present in group 1A, bromine is present in group 7A. 1A means it has uh, one valence electron, and we know any element which forms ion from group 1A gets a 1 positive charge. 7A, that's a non-metal, it's gonna gain electron. How many electron is gonna gain? Group number minus 8. So group number is 7, 7 minus 8, that's negative 1. So bromine will become Br negative, cesium will become Cs positive. So this is cesium ion, and this one is, it's bromide. Remember, ene becomes ide, so bromide ion. So what's going to happen is, cesium is transferring one electron to bromine. So cesium gonna lose one electron, bromine gonna gain one electron. Let's solve this problem. In this problem, we need to indicate the number of protons and number of electrons in the following ions. Before we solve this problem, please remember that in an atom, not ion, atom, number of protons is equals to number of electrons. Both protons and electrons are equal. Also, in an atom, number of protons is same as atomic number. So if you want to figure out number of protons in any atom, just look at its atomic number. It's same as the number of proton. And similarly, if you want to figure out how many electrons it has, again, look at the atomic number, because in a neutral atom, protons are same as electrons and they are both same as atomic number. However, in this example, we don't have neutral atom, we have ions. So let's take a look at iodide ion first. So in iodide, first of all, we need to figure out how many protons it has. Remember, when charges are generated, nothing happens to protons. Protons are not lost or gained. It's all about electrons. So therefore, this negative charge means it has extra negative now, means extra electron, more electron than proton. So in neutral iodine, if we look at the periodic table, so iodine atomic number is 53. So atomic number of iodine atom is 53. So it means number of protons is also 53. Now remember, nothing happens to protons. They are not lost or gained. So number of protons is same as 53. On the other hand, in case of neutral iodine atom, the electron would also have been 53 if it's an atom. But it's not an atom, right? It's a ion. An ion means it has a negative charge. Negative charge means one extra electron. So extra electron means 53 it already had plus 1. So therefore total number of electron now is 54. And that's going to be our answer. Similarly, if we solve for B, B is a phosphide ion with 3 negative charges. Again, if we look at the periodic table, phosphorus has atomic number equals to 15. So therefore, number of protons in phosphorus is also 15. Okay, so that's we've figured it out. Now, number of electrons in phosphorus atom. Remember, in atom, not this ion. So in atom, it would be 15. But because it has 3 negative charges, it means it has extra 3 electrons. It got 3 negative charges because it absorbed 3 extra electrons. So therefore, now the number of electrons would be equals to, it already had 15 to begin with, and plus it gained 3 extra, so total number of electrons it has now is 18. And finally, for lead is the other kind of ion. It has a positive charge, and we know that positive charges are formed when you lose electron. So atomic number of lead is 82. So therefore, number of protons is also 82. And remember, metals lose electron and they get the positive charge. So now it has 2 positive charge. It means it has lost 2 electrons. So to begin with, electrons are same as protons, but because it has lost electron, therefore number of electrons will be equals to 82 minus 2, because it's lost 2 electrons, so it's 80. So that would be our answer. Let's learn how to write the formula unit of an ionic compound. An ionic compound is represented by a formula unit which specifies the cations and anions that make up the ionic compound and their ratio. The atomic symbol for cation is always written first, and then it is followed by the atomic symbol for the anions. When we write the formula, we exclude the charges. See, these are the ions, but when we write the formula, we exclude the charges. And in the formula, subscripts following the atomic symbols in the formula unit indicates the lowest whole number ratio of cation to anion. For example, in case of sodium chloride, we don't see anything here, we don't see anything here. So if you don't see any number here, so that means it's 1. So in this case, the ratio in which the cation and anion are combining is 1:1, means for 1 sodium we need 1 chloride. And finally, remember that sum of charges on cations and anions must be equal to 0. So for example, in case of sodium chloride, sodium has 1 positive charge and chloride has 1 negative charge, so that together the total sum is 0. Another example of a formula of ionic compound is given for magnesium oxide. Magnesium oxide is made up of magnesium ion and oxygen ion, and again magnesium has 2 positive charge and oxygen has 2 negative charge, so charges are equal. So every 1 magnesium ion will be enough to neutralize the oxide ion. So therefore the whole number ratio in which they combine is 1:1, so that will be our formula. Let me explain a little bit more that imagine that if you have no idea what will be the charge and how they're gonna combine, then how you come up with the formula. Let's imagine So we want to write the formula of ionic compound formed by calcium and oxygen. Okay, so we need to write the formula of ionic compound which is made up of calcium and oxygen. So the first thing we need to do is we need to find the symbol for calcium, and if you look at the periodic table, so you will find calcium symbol is Ca. So write down the symbol for calcium. Then we need to find the symbol for oxygen, and that is O. Next part is we need to find the charges on calcium ion and oxygen ion. And we learned in previous slide that if the elements are in group 1a, the charge will be 1 plus. If it's in 2a, the charge will be 2 plus, and so on. And if you look carefully in the periodic table, calcium is in group 2a. So therefore charge on calcium is 2 plus. Similarly, for non-metals, the charges can be found group number -8, and oxygen happens to be in group 6a. So therefore charge on oxygen will be 6 minus 8, -2. And that's why in this oxygen also we have -2. Anyway, so it will be -2 here. So once you figure out the charges on the metal, so now you need to figure out how many ions of metal will be enough to neutralize the charge on the non-metal, which is oxygen. So remember, equal and opposite charges cancel each other out. So calcium has 2 positive, oxygen has 2 negative, so therefore the ratio, one of this will be enough to cancel one of that. So all you need to do is you put them together. So Ca1, because we need 1, and O1. Now we don't need write the charges here. Why? Because charges are cancelled because they are together now. And by convention, 1 is not written, so this is the formula. So these kind of compounds are called 1:1 ratio compounds. 1:1 ratio ionic compounds. Because in all of these compounds, cation to anion ratio is 1:1. Similarly, sodium chloride is also 1:1. Magnesium oxide is also 1:1. There are many compounds or ionic compounds in which the ratios will be other than 1:1. Let's take few examples. So if we write ionic compound formed between let's say sodium and oxygen. Okay, let's try to write its formula. We're gonna follow the same steps. So first step is write down the symbol. So that's Na for sodium and oxygen is O. Then figure out the charge. Sodium is in group 1a, oxygen is in group 6a. In previous slide we found that the negative charge on non-metals will be group number -8. So therefore oxygen is -2. And sodium charge is 1a, so it's gonna be 1 plus or just positive. Now sodium has only 1 plus, oxygen is -2. So 1 plus not gonna cancel the -2. So that's they are not equal, right? So equal charges cancel each other out. So it means 1 sodium is not gonna be enough to cancel a charge on the oxygen. So in order to cancel the 2 negative charge, we need 2 positives. So 2 positives means we gonna need 2 sodium atoms, because together 2 of them will be this much charge, which is +2, and oxygen alone is -2. So 2 of these together are strong enough to cancel out the charge of 1 oxygen ion. So therefore when they combine, so 2 sodiums, how do we show that there are two sodiums, we put a subscript here. So this subscript means we have two of sodium ions and one of oxygen, but we don't show one as I mentioned earlier. So the formula of compound between sodium and oxygen will be Na2O. Let's try another example. Let's try to write the formula between magnesium and nitrogen. Remember, ionic compounds are always between metal and a non-metal. Metals get positive charge, non-metals get negative charge. Now magnesium is Mg and nitrogen is N. The charge, magnesium is in group 2A, nitrogen is in group 5A. So metals get positive charge is same as the group number, so therefore it's 2 plus. Non-metals get the charge 5 minus 8, so in this case it's negative 3. Now as we can see, positive 2 is not going to be enough to cancel out the negative 3. So it means we're going to need more of magnesium. So if we have two magnesium, so together the charge is positive 4 and nitrogen alone is negative 3. It's still not equal. So this is still not going to work. Okay. So that's a little bit tricky situation. So in this case, the ratio which will work is it will be 3 magnesiums and 2 nitrogens. Why? Because 3 of these magnesiums together will be plus 2 plus 2 plus 2, which is equals to plus 6. And 2 of nitrogens will be negative 3, negative 3. This is negative 6. So now we can see that the charges are equal and opposite, so they will cancel it out. So therefore, formula of this compound will be 3 magnesiums, it means Mg3, and 2 nitrogens, N2. So this will be the formula. So we have learned how to write the formula of ionic compound. Next step is to figure out how to write their names. Writing the names of chemical compounds is known as nomenclature. And nomenclature is one of the most important skill in chemistry. So we need to know how to write names, and if the names are given, how to write the formula. Writing names of ionic compounds is pretty simple. The rules are, first write the name of the cation and then write the name of anion. And we do not include the information about the subscript. Subscript means how many ions are present. That information is not included in the name. If you already know the name, how to name cations and anions, good. But if you are having some doubts how to write the names of cations and anions, I'm going to simplify it a little bit more here. I'll explain with the help of an example. For example, let's try to write the name of a compound whose formula is CaO, right? So first we write the name of cation. So the name of cation is calcium. And then we're gonna write the name of anion. Remember, this is oxygen, but oxygen is the name for atom, neutral atom. But when oxygen is anion form, it's not called oxygen, it's called oxide. Okay, so it will be oxide. So if I have to generalize it, so how do I generalize it? So I'm gonna write a general formula. So for ionic compound, so this is the general formula you can use. So write the name of metal first, and then write name of non-metal, remove last 3 letters from the name, and then plus add the suffix IDE at the end. Okay, so let's put this into practice. Let's say I want to write name for this compound. Okay, so first I need to write the name of the metal, right? So name of metal is magnesium. Okay, so I'm done with this part. Next part is name of the non-metal. So name of the non-metal is nitrogen. Okay, and then we're gonna remove the last 3. Okay, let me modify it. Some cases it's 3 or 4, but with you, when you practice, you will understand it. So we're gonna remove last 3 or 4 letters. So in this case, ogen is removed, so that goes away, and then we add ide at the end. So that's a name, magnesium nitride. Similarly, let's write the name of this compound. So in this case, first we're going to write the name of metal. So name of metal is calcium. And then name of non-metal is bromine. But we're going to remove the last 3 letters. Okay, that goes away. And we're going to add ide at the end. So the name is calcium bromide. And using this trick, you can write as many names as you want. So in case our metal is from the transition metal category, or the ones which have more than one charge, then we use the Roman numeral in the middle. So this Roman numeral is used to indicate the charge of the metal. For example, iron in this form, iron, first you need to figure out what's the charge here. How do we figure it out? So the way we figure it out is, so we just imagine that these two things are separated. We have to imagine. So when they are separated, so 2 means we have 2 chloride ions. And we know each chloride ion is 1 negative, right? So, and we have only iron. So if 2 of these together will be 2 negative, so therefore iron must be 2 positive, because positives and negative charges has to be equal. Okay, so in this case, again, we're gonna write the name of the metal, which is iron, but because it belongs to a category where metals can have more than one charge, so we put Roman numeral in the middle to indicate that its charge is +2, and then non-metal is chlorine, but we're gonna remove the ene and we're gonna add ide, so iron 2 chloride. So this table summarizes all the rules as well as it gives examples of various ionic compounds with monoatomic cations and anions. Just remember that in the name, first we write the name of the metal with no changes, and then name of non-metal with ide at the end. So bromine becomes bromide. Another thing to remember is the name does not indicate how many ions are there. Even if there are 2 ions, 3 ions, does not matter. So therefore we don't tell that there are 2 bromides or dibromides. That's not necessary. And in metals where they can have more than one kind of charge, in those metals we do use Roman numerals in the middle. Ionic compounds are found in many foods and other consumer products. For example, Calmetine lotion, this one as used as shown here, contains zinc oxide, and this is the formula of zinc oxide. And And zinc oxide soothes the irritated skin. And similarly, uh, sodium fluoride is an additive to many toothpaste. So, and formula of sodium fluoride is NaF. And sodium fluoride is used because fluoride ion, this ion, it strengthens the tooth enamel and it prevents cavities. The same zinc oxide is also used in many sunscreen creams or lotions because the zinc oxide also blocks the harmful ultraviolet rays from the sunlight. Let's practice writing the formula units for some of the names. So first one is sodium sulfide. So sodium sulfide means it's made up of sodium. So first we need to write the symbol for sodium, and sulfide means it's the non-metal is sulfur. We don't simply put them together and then call it a day. No, that would be incorrect. Let's not do that. We need to figure out the formula. So before we figure out the formula, we need to write the symbols as we did, and then we need to figure out the charges. Sodium is in group 1A, so its charge is 1 plus, and sulfur is in group 6A. So therefore we know that the charge of non-metal will be group number -8, so it will be -2. So now we need to figure out if they're gonna balance each other out in ratio 1:1, 1:2, or 3:2. One of these three ratio will work. And I can clearly see that 1:1 not gonna work. Why? Because one sodium not enough to balance one sulfur. The ratio which gonna work is 1:2 because two sodiums will be enough to balance two negative. So therefore, because it's 1:2, or you can also call it 2:1, same thing. So therefore the formula will be Na2S. Next one is magnesium nitride. Again, you write the formula of magnesium. Nitride comes from nitrogen. Figure out the charges. Magnesium is in group 2A, so +2. Nitrogen is in group 5A, so therefore 5 minus 8, -3. In this case, if you see 1:1 not gonna work, 1:2 not gonna work. In this case, 3:2 will work because 3 magnesiums and 2 nitrogens will be enough to cancel each other out because 3 magnesium is +6, 2 nitrogen is -6, so they cancel each other out. So therefore the formula will be Mg3 and 2. Please remember these numbers are subscripts. If you write this way, Mg3 and 2, that would be incorrect. So the correct way of writing is this way. So this is correct and this one is incorrect. Number C is copper 1 chloride. So it's a copper, again symbol is copper, and this 1 means its positive charge is 1. Chloride come from chlorine, and we know chlorine has a charge of -1 because it's from group uh, 7. So 1:1 will work here because 1 positive, 1 negative. So therefore their formula will be CuCl. And then the last one is copper 2 chloride. So copper 2 means copper has a 2 plus charge and chloride is still the same, -1. So copper is 2, chloride is -1. In this case, 1:2 ratio will work. So the formula will be CuCl2. Let's practice writing names of few ionic compounds. The first one is again write the name of metal and name of non-metal minus 3 or 4 last letters plus IDE at the end. Okay, so in this case, name of metal is sodium and non-metal is oxygen. So we're gonna remove last four letters and we're gonna add "ide" at the end. So the correct name will be sodium oxide. In this case, name of metal is magnesium. Iodine, we're gonna remove the last three letters and we're gonna add IDE, so magnesium iodide. Similarly, metal is potassium and chlorine becomes chloride. Zinc, although zinc is in transition metals, but zinc is one of those transition metals which always have +2 charge, so we do not use Roman numeral for zinc in the name, so we don't use this. Okay, other transition metals we do use Roman numeral, so zinc, and then oxygen becomes oxide. All the ionic compounds we have seen so far belong to the category of ionic compounds containing monoatomic ions. The second category of ionic compounds is those which contain polyatomic ions. Poly means many, so therefore polyatomic ion is an ion derived from a molecule rather than a atom, because polyatomic means many atoms within an ion. A polyatomic ion contains multiple atoms connected together with a bond, multiple bonds, but the unequal number of protons and electrons create a net charge. One of the most common polyatomic ion example is sulfate. There are many other, but let's go with this example first. So as you can see, within this entire ion, we have one sulfur atom and four oxygen atoms, and all of them are connected with each other with multiple bonds. But overall, in the entirety of this whole entire element, uh, there is a mismatch of number of protons and number of electrons. Hence, we have a 2 negative charge. Now, if you are wondering where this 2 negative charge is it on sulfur or is it on one of the oxygen? So at this point, you can consider that the charge is shared by all the atoms within this polyatomic ions. It does not belong to one individual at this point, so it's shared completely. So this 2 negative charge belongs to the entire ion. Each polyatomic ion has a unique name, unique formula, and a charge, which you should learn. And this technique of remembering the names and formula of polyatomic ion is extremely crucial for naming those ionic compounds which contain polyatomic ions. Some of the common examples of polyatomic ions is sulfate, as I mentioned earlier. So sulfate has a formula of SO4 and charge of 2 negative. Nitrate, it has formula of NO3 with 1 negative charge. Some polyatomic ions do have a positive charge also. For example, ammonium. So this would be the formula and the charge. And there are many more. So to summarize, we can say that polyatomic ions are derived from molecules, not individual atoms. They contain one or more covalent bond, and because they have unequal number of protons and electrons, hence there will be an overall charge. And each polyatomic ion has a unique name, formula, and a charge. For example, ammonium has a formula of NH4 charge of 1 plus, and carbonate ion has a formula of CO3 and the charge of 2 negative. Some of the common polyatomic ions are listed in this table. It will be great if you can memorize all the names and formulas, and I understand that it is quite tricky because some of the polyatomic ions and formulas are quite similar. For example, nitrate and nitrite, you can see they are quite similar. Similarly, sulfate and sulfite are also similar. So it's a good idea to start memorizing maybe one or two polyatomic ions a day, and within a week you will memorize most of them. Writing the formula of a ionic compound containing polyatomic ions involve the same procedure as described for monatomic ions, except the use of parentheses. Let me explain with the help of an example. For example, if in a monatomic ionic compound, if we want to write the formula of magnesium ion with chloride ion, so we know that the ratio gonna be 1:2 because 2 chlorides will be needed for 1 magnesium, and we write magnesium, we don't write 1 and Cl, and then we put subscript here, uh, uh, 2. Similar situation is here. If we want to write down the ionic compound between magnesium ion and hydroxide ion. Now hydroxide is a polyatomic ion. As you can see, we have more than one, and it has one negative charge. Again, in this case, you will see that one of hydroxide is not enough to balance the charge of 2 plus in case of magnesium. So we will need, again in this case, 1:2. So we will need 2 hydroxide to balance 1 magnesium. Right, so 1 negative from here and 1 negative from here, so total will be 2 negative. But when we want to write the formula, if you write it like that, it will be incorrect. Because why this is incorrect? Because if you leave it like that, it means that there are only 2 hydrogens and 1 oxygen, which is not the case. What we are saying here is that we have 2 hydroxides, so therefore we write parentheses here and then put 2 outside. The meaning of parentheses is that the entire polyatomic ion unit is repeated twice, or in other words, we have 2 hydroxides connected to 1 magnesium. So that's the only difference when we write the formula unit of ionic compounds with polyatomic ions. Otherwise, all the rules are same as monatomic ions. Naming of ionic compound with polyatomic ion is even more simpler than monatomic ion. In this case, we write the name of metal first, and then we write name of polyatomic ion as such. No changes, no ide, no subtracting, no addition, nothing is done, just as such. For example, in case of the example we saw in previous slide, in this case name of metal is magnesium and polyatomic ion is hydroxide, so the name is magnesium hydroxide, and that's it. In this case, name of metal is sodium, and CO3 is polyatomic ion, name is carbonate, so name is sodium carbonate. In case our metal has a tendency to form multiple charges such as iron, then we use the Roman numeral in the middle. For example, okay, so now iron belongs to the category which forms multiple charges. So here we need to write, so we cannot simply leave it like that, iron nitrate. So that would be incorrect because iron needs to have a Roman numeral in the middle where we show what is the charge. So it means first we need to figure out the charge. So how do we figure out the charge? Same principle as we figured out in earlier case. So we have iron as a cation and nitrate as anion, and we know from the table nitrate has a 1 negative charge. And how many nitrates do we have? This row, this subscript 2 indicates that we have 2 nitrates. So 2 nitrates means the total negative charge is -2. So therefore iron must be +2. So now we figure out the charge on iron. So therefore the name will be iron parenthesis 2 Roman numeral and then nitrate. Polyatomic ions are also common in nature and consumer products. For example, the active ingredient in bleach is hypochlorite, and that's the formula of hypochlorite. This iron hypochlorite is a bactericide, which means it kills bacteria, and that's why we use bleach to disinfect surfaces or even clean our clothes. Sodium nitrate and sodium nitrite are used as preservatives. So this one contains polyatomic iron nitrate, and then this one contains nitrite. Both are used in as a preservatives for our food items. These polyatomic ions inhibit the growth of microorganisms such as fungus and mold. Our tooth enamel, as shown in this picture, contains a polyatomic ion named hydroxyapatite. In fact, it contains a ionic compound with polyatomic ion calcium hydroxyapatite. And this compound is made up of a polyatomic iron phosphate as well as hydroxide. So interesting fact is that in natural tooth enamel we have this compound calcium hydroxyapatite, and in this case we have hydroxide as a polyatomic ion. It turned out that if instead of hydroxide we have a fluoride in this compound, so we get this new compound. So this is much more stronger than the original tooth enamel. So therefore many toothpastes have fluoride in it, because fluoride from the toothpaste, it will kick out the hydroxide and replace it, which makes our enamel strong. Many municipal water supplies also have fluoride in it in order to prevent the tooth decay, because tooth decay could be a reason for bacteria growth and whatnot, and it may lead to other health diseases. So that's why it's a good idea to replace hydroxide with fluoride. Let's practice with some examples of ionic compounds with the polyatomic ions. Remember, when we want to write the name of polyatomic ionic compound with polyatomic ions, we write name of metal first, and then we write name of polyatomic ion. Let's apply that concept and figure out the name. So for A, metal is sodium, so I'm gonna write sodium, and the polyatomic ion is OH, and I know from the table that OH is hydroxide, so the name is sodium hydroxide. In second example, the name of cation or the metal is silver. Now, although silver is in transition metal category, but it forms only one kind of charge, so we don't use Roman numeral here in case of silver. Remember, silver and zinc are two exceptions where we don't use the Roman numerals. So silver and NO3 is nitrate, so the name is silver nitrate. In C, it is a little bit unique because there is no metal. So maybe I should modify my general formula here, name of metal or cation, because generally metals are cations. In this case, the cation is also a polyatomic ion. So NH4 is ammonium, so the name would be ammonium, and CO3 is carbonate, so it's ammonium carbonate.